So welcome class to our session. So this is design of steel structures. I'm Engineer Ronjon Argarmi. So today we are going to discuss the concepts and formulas plus sample problems regarding tension members. So tension members are force members in axial tensile force. So it could be present in the members of the truss. Of course, the truss has a merged triangular configuration wherein the force members could be in compression or in tension. So tensile members also present or could be found on bridges and building braces. So of course, in cables of suspended roof systems or in cables of suspended bridges. So for large loads, build-up shapes is desirable because a single member or a designed single member could not be sufficient enough because in the previous session we have mentioned that we have standard shapes, okay, wherein those standard shapes could no longer resist the required loading. So in that case, normally those standard shapes, steel shapes, would be combined together and combined with the other elements like plates in order to have a supplement on the cross-sectional area so that it could resist larger loadings. So build-up shapes could be the plates, the rolled shapes, or the combination of both. So these are examples, typical examples of those build-up shapes. As you can see, we have the rolled shapes. So the plates are bended to form a tube, circular tube, a rectangular tube. So rolled shapes could also be combined to the other one, okay. And of course we have the common steel shapes like angle, channel, or S shapes. So we can see here a build-up shapes the combination of the angle, and this is what we call the double angle build-up shapes. So likewise for the channels could be connected by a plate, okay, that is symmetrically placed on between those channels, and that will be a build-up shapes. Of course, when we have a build-up shapes, the moment of inertia and the area will be enlarged through the build-up shapes concept. So tension members will be calculated with a simple formula coming from the concepts of stress. So this is actually the axial stress. The axial stress is denoted by sigma is equal to the tensile force P all over A. So this is also true to compression members. Steel shapes as structural elements are normally at its far end. Of course, those members will be interconnected at its joints or the point of intersection, especially on frames, trusses. The presence of holes is influential to the net area, thus affecting the stress of the member. Of course, if you are going to connect that by a bolt, so the space occupied by that bolt will reduce the net area of your cross-section. So if we consider here a connection between a bar and a member. We have the diameter of holes and given the bar with its thickness. So at section A, your net section is still whole, or it's not reduced in a sense that there is no presence of hole or bolt in that cut section AA. So meaning your net section will be 8 by 1/2, or the width times the thickness. While if we are going to consider here the section on the hole with the presence of the bolt in it, section BB, we can see that your net section is now reduced by that hole that is occupied by the bolt. The tensile strength is given by this formula. Sigma is equal to P over A. If we are going to cross multiply that, we can come up with the allowable load on the member, considering the strength sigma. Now, sigma for yielding is what we call Fy. So, when we say yielding, the strength is at the verge of deformation. So, there is no deformation yet. And then, if the load is increased further, it will be subjected for fracture, wherein the concentration of the loading will be on the holes or on the net sections that are reduced, of course, wherein the cracking would be now evident. So again, the sigma for yielding is termed as Fy, and the sigma for fracture is F sub U. So this came from this formula. If we are going to utilize this formula, sigma A, we will have that P, or that loading, should always be less than the product of its strength times the cross-sectional area. Hence, considering Fy, the nominal loading Pn, P sub n, will be equal to Fy, or the strength sigma, on the yielding times the gross area. So the gross area is the net area that was not yet reduced, or there will be no presence of holes occupied by any bolt. While on the fracture, P sub n will just have to replace the sigma by Fu multiplied by the net area. So the net area now is the reduced area because of the holes occupied by that of the bolt. And that is what we call the effective net cross-sectional area. So the A sub G is cross-sectional area. So in here, I would like to present the yield strength of the commonly used sections. We have namely A36, A572, grade 50, or A992. So this is according to the AISC code, and it was also discussed in the previous sessions. Okay, so this is assigned by the American Society for Testing and Materials. We have here the yield point minimum, the tensile strength minimum, the yield to strength ratio, the maximum, and the elongation in 8 inches. This is minimum. So basically, in most cases, A36 steel is commonly used. Let us take note on the yield stress. The yield stress is Fy. That will be equal to 36,000 psi, equivalent to 36 kips per square inches. While the tensile strength Fu is equal to 58,000 psi, pounds per square inch, or that will be equal to 58 kips per square inches. So A36 steel is classified as a plain carbon steel. So it has the following components. Okay. So our concern here is the Fy and the Fu. So the yield stress and the tensile strength. So this is Fy and that is Fu. So considering the load and resistance factors design as a design load, we agreed last time that Ru should be less than or equal to the phi Rn, wherein Ru is the sum of all the loadings, whether it is an actual load or a couple. So this must be compared to the factored resistance, phi Rn, and phi Rn is called the design strength. Hence, we can write that into the load form, wherein Pu, so the ultimate load, should always be less than or equal to the factored load P sub n. So phi is equal to 0.9 for yielding, while phi is equal to 0.75 for fracture. So we will come up with a formula that Pu shall be equal to 0.9 of FyAg, while for fracture, Pu is equal to 0.75 of Fu times the effective area. Notice here that Fy is always paired to that of the gross area, while that Fu is always paired to your effective area. For allowable strength design, the design load is governed with this equation. Ra is always less than that the nominal resistance all over the factor omega. So we concentrate ourselves to this right hand side of the equation. We can write that as the nominal load all over omega, wherein omega for yielding is equal to 1.67. Hence we can write this formula. So the ratio of that Pn all over omega is equal to Fy Ag all over 1.67. Hence, we reciprocate 1.67 becomes 0.6 multiplied by Fy times the gross area. For fracture, we use omega is equal to 2.0. Again, for fracture, Fu is always paired to that of the effective area. Hence this equation. Now, reciprocating 2, that becomes 0.5. So therefore, the allowable strength now will be equal to 0.5 FU times effective area. So this is the equation wherein we get for the allowable strength for the fracture. So before we'll start with sample problems, knowing those equations, we should be aware about the bolt nominal area. So I'd like to present here a table coming from AISC that the standard diameter shall include an increase in the nominal area. So what I mean is that when we calculate the area here, we should take note that the diameter is not the width itself, but we should have to refer to this table. For example, if the bolt diameter is 1/2 and then we cross section that, we should not use 1/2 but rather use 9/16 or 5/8 inches diameter. Instead of using the width 5/8, we use 11/16, and so on and so forth. For a bolt diameter greater than or equal to 1 1/8, all we have to do is to add 1/8 to your diameter, which is actually adapted in any problems of steel design. In most books, whatever the diameter is, all we have to do is to add 1/8 to come up with the nominal width or diameter of your bolt when computing for the effective area. So again, for problems in the books, we should always add 1/8 to our diameter. But in practice, we should refer to this table J3.3. So likewise, in SI units, we have the following: standard diameter and effective diameter. So dealing with SI, all diameters will just have to add 3 millimeters. So moving on to sample problems. In here we have a 1/2 by 5 plate of A36 steel is used as a tension member. It is connected to a gusset plate with 4 pieces of 5/8 inch diameter bolts as shown in the figure. We have to assume that the effective net area equals the actual net area. So first requirement, what is the design strength for the load and resistance factor design? And what will be the allowable strength for ASD? By the way, if we have to deal with LRFD, so the term for the strength is the design strength, while dealing for ASD, the term is the allowable strength. So this is now the figure. So the plate is connected through a 4, 5, 8 inches diameter bolts. Okay, so basically this is the cross section having a thickness of 1/2 inch. So we take note we are using a 36 steel, so we will use Fy 36 KSI for yielding, and Fu is equal to 58 KSI for fracture. Now, working with the first requirement, for yielding of the gross section, we have to compute for the gross area. So we have here 5, so the width is 5, we have the thickness, so therefore that would be equal to 2.5 square inches for the gross area. So gross area will be used for yielding. So for the fracture of the net section, AN will be equal to the gross area minus the area of the holes. So the gross area is 2.5, and considering the holes, of course, this is what I'm talking about earlier. We should have to add 1/8 to your diameter. So the diameter here is 5/8. We add 1/8, that would yield to 3/4 inches. So of course, we have to multiply 1/2 thickness to deduct that area occupied by that bolt, and that bolt has 2 holes. Okay, so there are 2 bolts, there are 2 holes. So 1/2 the thickness, 3/4 is the effective nominal diameter, times 2 holes. Again, 3/4 inches is derived by adding 1/8 to your bolt diameter 5/8. So we'll come up with 1.75 square inches as our net area. So in the problem, it mentioned that your effective net area would be equal to the actual net area. Hence, we can now compute for yielding that P sub n is equal to FYAG. So all we need is to multiply that by the gross area. So 36 times 2.5 is 90 kips. So phi for yielding is 0.9. Phi Pn is 90% of 90, and that would equate to 81 kips. Now for fracture, we have Pn is equal to Fu times Ae. So it mentioned that Ae will be equal to A sub n. Hence, we'll just have to multiply our Fu 58 to that of the effective area, 1.75. So that would yield to 101.5 kips. So we apply the resistance factor 0.75 for fracture. So phi Pn is equal to 0.75 times 101.5. So finally, phi Pn is equal to 76.1. So between the two, yielding and fracture design strength controls. Therefore, we can choose that as our design strength for the configuration. Now for our letter B, allowable strength design. Okay, we'll just have to take note of the strength of A36. So just the same, we compute for the gross area. Okay, 2.5 square inches. So similarly, we compute also for your net section, considering the addition of 1/8 to your bolt diameter. There are 2 holes in that. So we have the same AN and AG, wherein AN, according to the problem, is also your effective area. For yielding, we do the same calculation for PN, FYAG, 36 times 2.5. That would yield to 90. So notice that we have the same procedure to that of the LRFD. Only that we translate your design loading to allowable P sub n, and that will be equal to 0.6 of FYAG. FYAG is actually the nominal P. So therefore, the allowable P sub n is equal to 60% of your P sub n. So therefore, the allowable strength is equal to 54 kips. So for fracture, we do the same calculation as for PN in LRFD. Okay, 58 times 1.75, that is 101.5 kips. So we just have to multiply that by 0.5 for fracture in ASD. So we come up with the allowable P sub n, 50% of 101.5, that is 50.75 kips. So in this example for ASD, 50.75 for fracture is less than that of 54 kips. For the allowable strength, we always choose the less value between the yielding or the fracture. Hence, the allowable strength for ASD here would be equal to 50.75 kips. So moving on to the next example. So in here we have a single angle tension member, L3 1/2 by 3.5 by 3/8 thickness, is connected to a gasket plate with 7/8 inch diameter bolts, as shown in the figure. So again, A36 steel is used. The service load will be equal to 35 kips for dead load and 15 kips for live load. So our task is to investigate this member for compliance with the AISC specifications. Assume that the effective net area is 85% of the computed net area. So in this case, we have given service loads. Of course, we have learned in our previous session how to compute the combinations by LRFD or by ASD combinations. Let us take note that these service loads or each combinations should be always less than that of the allowable strength or the design strength. So A36 still has Fy of 36 KSI, and again it has Fu for fracture equal to 58 KSI. Now in here, your area is not given but can be found in Steel Handbook. So in Steel Handbook, you can see a lot of cross-section because again, these steel shapes are standards and all of its properties are tabulated in the Steel Handbook by AISC and ASTM A-36. So we just search for your section, and that is L3.5 by 3.5 by 3/8. So you can see that the area is on the 4th column So on the fourth column of your cross section, we have 2.5 square inches. Okay, so knowing that, we have now the gross area equal to 2.5 square inches for yielding. Okay, now for fracture, we subtract your holes. So first we have the gross section of 2.5. We less your thickness multiplied by the bolt diameter plus 1/8. Okay, so therefore the net area will be equal to 2.125. Hence we can derive the net area according to the problem is 85% of the computed net area. So therefore the effective net area is 85% of 2.125, and that would yield to 1.806 square inches. So using now LRFD, knowing your area, gross area, and the effective area, similar procedure will be conducted. So P sub n for yielding, always remember that we just have to pair Fy to that AG. Okay, so we just multiply 36 by 2.5, will arrive at 90 kips, wherein the factored resistance, you just have to multiply 0.9 to your nominal load Pn. So therefore, we have Vpn is equal to 81 kips. That is for yielding. So of course, we should have to compare your design loading with that of the service loading or the actual service loading. So in here for LRFD, we have two load combinations that are applicable. We have 1.4 dead load and 1.2 plus 1.2 dead load plus 1.6 live load. Of course, between the two, combination 2 prevails, okay, with the value of PU or service load equal to 66 kips. So 66 kips, since your service load 66 kips is less than your 81 kips, therefore the member is okay, hence it is compliant to AISC specifications. So meaning your member still can resist the service loads given. Okay, so that is for yielding. For fracture, considering the fracture, we do the same. We have the gross area 2.5 square inches and the calculation of the net area, and that net area is 85%. Okay, getting the 85% of that net area, we have the effective area 1.806 square inches. So for fracture this time, again, for fracture, let us bear in mind that we always pair Fu to that of the A sub E, FUAE. So we multiply 58 by 1.806, we have 104.7 as our nominal load. And then for the design load, we should have to multiply that by 0.75. So we get the 75% of your nominal load to get the design load. Hence, that is Vpn equal to 78.5 kips. So again, this must have to be compared with your service loads, wherein combination 2 prevails on the related combinations of dead load and live load. So we compare 66 to your 78.5 kips. Therefore, your service load is less than your design load. That is okay. Hence, the member is compliant on the design load with respect to fracture. Okay? So, moving on to the ASD. So, for ASD, again, we take note of the strength of A36 steel, 36 KSI, and 58 for FU. So, we have the same cross-section. We have the gross area. Just the same. We need to compute for the effective area. That is 85% of your net. That is according to the problem. Now, for yielding, we do the same process. Compute for the nominal loading PN. That is 90. And all we have to do is to multiply it by 0.6. Okay. So, now, the allowable load will be equal to 60% of your FYAG, or the nominal loading. So that is 53.9 kips for yielding. So we compare this to the combination of the service load for ASD. So ASD has no load factors. Simply adding your dead load and live load, that will be equal to 50. So in comparison, your service load PA is less than your allowable PN. Okay, 50 kips is less than 53.9 kips, and that is compliant to AISC specification. So for fracture, using ASD, we have the AG and the effective area AE. So we just pair your FU to that AE, 58 times 1.806, so 104.7 kips, and then multiply that by your omega, or the reciprocal of your omega, that is 0.5, okay, for fracture. So therefore, the allowable load will be equal to 50% of your FYAG, or FUAE. So let me correct this, FUAE. 0.5 of 104.7. That is 52.35 kips. And again, comparing that to the sum of your dead load and live load, 50 kips, still that is greater than your service load, 50 kips, and that is still compliant, and failure would not be observed because your member could still resist the service load in terms of fracture strength using ASD. Okay, so next problem, this time we have the double angle shown in the figure. Again, we use A36 steel. So we have 1/2 inch diameter bolt. So we assume that your effective net area is equal to 75% of the computed net area. So using LRFD, by the way, we will determine here the design's tensile strength, okay, and determine the allowable strength for ASD. So this is the cross section. So this will now be an example of the built up section. We have here the double angle. So that is denoted by 2L5 by 3 by 516 LLBB. In here, we refer to the table once again. So this is L5 by 3 by 516. We have the area to be equal to 2.41. So this is the area for a single angle section. So what we do is to compute it as it is, and then later we double the result of the strength. So using LRFD, so we note that the gross area from the table is 2.41 square inches. Now for fracture, the net area will be equal to 2.41 less your thickness multiplied by your diameter of the bolt, 1/2. Of course, we always add 1/8 on that diameter. So we'll come up with 2.019 square inches. So according to the problem, 75% of your A sub n will be your effective area, and that will be equal to 1.514 square inches. So knowing those AG and AE, we can now proceed calculating your P sub n FYAG. 36 times 2.41, that would yield to 86.76. So for LRFD, the resistance factor for yielding is 0.9. We have to multiply 0.9 to 86.76, and that will be your design load for yielding. And then for fracture, we have here P sub n 58 times 1.514. That will yield to 87.81. We have the resistance factor for fracture, 0.75. And then VPN is 0.75 times 87.81. We will have a design load for 65.86. So again, we have the comparison of yielding and fracture. Again, 65.86 is less than your 78.08, obviously. So therefore, we can say that between those strength of yielding and fracture controls because it has the lesser value. And then the design strength will be twice of that value. Why twice? Because we have the double angle. Hence, 131.72 kips will be chosen as our design tensile strength, considering the load and resistance factor design. Now for ASD, we have the same pattern of solution. First, we need to compute for the AG and then AN, and then the effective area, which is 75% of your net area calculated. Now for yielding, that's the same. We can compute for P sub n FYAG. Okay, we come up with 86.76, and that shall be multiplied by 0.6. Okay, so therefore, you have the allowable loading PN, 60% of 86.76 equal to 52.06 kips. That is for yielding. While for fracture, again for fracture, we pair FU to that of the AE, FUAE. Then P sub n is equal to 58 times 1.514, the net area. We have the result 87.81 kips, and then we'll just have to multiply that by 0.5. Okay, So we come up with the allowable PN 43.91 considering the fracture. Now the fracture controls here because the allowable PN from the fracture, derived from the fracture, is less than that of the yielding. So fracture controls in ASD. So therefore the design strength is 43.91. We choose that lower value and multiply it by 2. Again, we double that because we have here the double angle or the build-up section. Therefore, we have 87.81 kips as our allowable strength for that build-up section. Okay, so that ends our session for today. So see you next time, and thank you for listening, class.